Okay, we have been talking about exponential functions. So as kind of a review, an exponential function is when I have a chart that looks like this. If I repeatedly multiply by something, so this is 15, this is 45, and 45 times 3 is 135. Okay, so we are repeatedly multiplying, going from one to the next. We multiply by a consistent. It grows fast. This is a growth function. 1, because if I look at the numbers, they are growing as I go from 0 to 1 to 2 to 3. They are growing. So it's called a growth function. And notice numbers start out pretty small, but as you get up into larger ones, if I were to multiply this by 300, what is it?
It'd be like 405, I think. Maybe.
405, that might be right. Yes, it is. Okay, notice that it grows a lot faster. So here, it actually grew by 10, here it grew by 30, here it grew by 90, here it grew by 90 times 3, 270, okay? So it grows a lot faster, and that's what a growth factor is. It's not linear. Comparing this to a linear function, a linear is y equals mx plus b. So what it looks like is if I have 0, if I have 5, 1, 7, 2, 9, 3, 11, we are adding to, and notice it's a nice constant rate. It's a constant rate. It doesn't change how much we're adding each time. So this is a linear function because it's growing. It's just not growing exponentially. Okay. So that's the difference. 1 is if you look at the differences here, they're added. If you look at the difference here, they're multiplied. So the difference there are those two things. Okay. So growth functions are defined when the growth factor, so it's called the growth factor, I call it the base, is greater than 1. Because when I multiply by anything that's larger than 1, things will grow. Okay? Every time I multiply by something greater than 1, it makes the number bigger. So it is going to be a growth function. Okay? That's what we looked at. Growth functions are usually things like population. That's one idea of a growth function. A growth function can be the number of bacteria or the number of viruses, okay, which really are populations. These grow a lot easier for you to see. Okay, populations of states and stuff, there's a whole bunch of things that influence them. Populations of rabbits and all those kind of things, again, a lot of factors that influence. These will continue to grow if they're not stopped somehow. Your body tries to stop viruses. It's pretty successful. It may take a few days for it to do it, but it's pretty successful. Bacteria, you have to have an antibiotic to help stop that, because it will grow really fast, repeatedly. Sometimes your body can fight it, but you have to be in pretty good, your immune system has to be pretty good to fight bacterial infections. But if you think about, okay, you guys are gonna love this. If you get a little pimple, okay, most of the time that is a bacterial infection. You don't have to go get usually an antibiotic to take care of that little pimple. Your body will attack it and kill it. It's just not one that grows real fast. okay, it's speed of rate. Yes,
I have an infection in my toe. I might
Okay.
have to get it like removed.
the toe?
No, not my toe.
Oh, the foot.
The part that's on it,
Yeah.
the infection, what they do is they take the infection out so it doesn't spread. Yes, that is something you do. And they'll probably also give you an antibiotic to
Yeah,
help make
thank
sure
you.
it doesn't come back. Yeah, okay. Yes,
Max has a question.
thank you, Grayson, so
But also,
sweet.
wouldn't mitosis also be on there?
Mitosis?
Yeah, it's basically like the doubling of cells.
Oh, yes, thank you. Thank you very much for that. Mitosis. I know why I didn't put it on here, because I don't know how to spell it. Is it like this?
Well, Matthew's not
I think
here,
so,
so.
Mitosis. I think that's how it is. Yes,
Is strep throat considered a bacteria?
yes.
I thought it was a
Strep.
virus.
Nope, strep is a bacteria. That's why you have to give an antibiotic. A lot of things mimic strep, and those can be viruses, okay? We do have antivirals. They're not like an antibiotic where they actually
Oh,
kill everything. But it usually can help if you get a really bad, nasty virus, then it can help with that, antivirals can. Okay. COVID was a virus. Okay. It's the coronavirus. That's what COV stands for, coronavirus of year 19. So when they say COVID-19, that stands for the coronavirus date 19. Okay, that's what COVID stands for. The coronavirus date of 19.
is that 2019?
Yep, 2019, because that's when it started, was in year 2019. So that's why it's called COVID, because it's just a shortening of those kind of things. It came in 2019. Okay, so that's how they identified it. It is a virus. There is no antibiotic that will kill it. What they do is they try to build your immune system so your immune system can do it. Or they give an antiviral. That's what they were giving people, was an antiviral. If your body wasn't attacking it as much, they gave you an antiviral to help your body fight it. Okay. Yes, there's all sorts of other things they say that you can use, but really what those things were stuff that can build your immunity, and so it will help your body to fight that virus. We do not have, like antibiotics, we do not have something for every virus. There are 1 million or more viruses out there, so we can't make a specific thing for each virus right now. Bacterias are limited, and the antibiotics work on most bacteria, but they will test to see what type of bacteria you have, and they know which antibiotic works better on certain bacteria than others. Okay, so that's what we use exponential growth for. So today we're going into exponential decay.
My bones
No, your bones are not decaying.
I'm sure we found I know.
Okay.
Oh.
Exponential decay. This is where things are decaying as you go through. This is where we talk about drugs. This is where we talk about how much carbon 12 or 14 or whatever carbon they check for dating. So when we do carbon dating.
Or depreciation.
Depreciation, thank you. Depreciation means how much is the value of a car, a house, anything that you have, how much does it go down? Okay, so that's what depreciation is. So these are things that we use, they're decaying, they're going down. They're not multiplying up, they're coming down. They start high and then it comes down. Okay, so when we do an exponential decay, the base is going to be less than 1, but not negative. In other words, it's going to be fractions, proper fractions. The decay number is going to be a proper fraction. Which can also, remember, all proper fractions can be written as percentages also. Okay, so when we're talking about exponential decay, we're actually talking about what is the amount that it decays in whatever specific time period that you have. Okay, so if you're looking at one, it would look like this. Let's start out with 32. Whoops. Okay, I think that's right.
2, 2.
Well,
Yeah,
yeah,
but
that's
you
to
go
say, I don't know what I'm doing. Yeah. There we go. So what am I actually doing from here to here? What am I multiplying by?
Dividing.
I'm dividing by what?
2.
Well, what is the same thing as dividing by 2? Yeah.
Multiplying by 1/2.
Multiplying by 1/2. So if you divide by 2, you're really multiplying by 1/2. Because it's going down by 1/2 each time. Okay. So my base, notice that's a proper fraction. 1/2 is a proper fraction. It is smaller than 1, but larger than 0. Okay. So in this, my decay is 1/2. My base is going to be 1/2. Okay. Where did I start? Yeah.
32.
I started at 32, right? So the equation for this will be y equals 32 times 1/2 to the x. Because see my base there? Again, starting number. This is our starting number. This is our growth rate. So it's starting number, and this is my growth rate. But because it's a decay, it's going to be a fraction or a percent that's less than 100%. Okay. Now, there's some tricky things when we're working with exponential growth and decay, which I'll get into that more tomorrow. Okay, look at the book. I gotta see what this section actually covers. Okay, some of this if I say something increases by 25%. If it's increasing, is it growing?
Are we still doing 7.3
I don't think so.
or 7.4?
It's 7.3.
Nothing.
If it increases, okay, I'm just asking, these are two different statements. Or decreases. One of these is a growth, one of these is a decay. Which one do you think is growth and which one do you think is decay?
This feels like a trick question.
Does it? Okay, it's
Wow.
not.
Okay.
Yes, Matt.
The increase. I mean, like the one not decaying is the increases.
Okay, this is the growth.
Not decaying is
This is a,
Yeah, I don't know what else to
Okay.
say. I was blurring it.
Oh, man.
but look at my
That's so
percent. It's the same in both cases. That doesn't make sense, does it?
I mean,
Because what did we say about growth? Growth has to be larger than 1. Okay? So 25% can't be my base, right? Because it's not less than 1. Or it's not more than 1. Yes.
increase would like have an implied 100%.
Yes, it does. You start with 100% and you add 25%. So when you're talking about increases by 25, it's 100% plus 25, which says you're going to have 125%, which that's 1.25, which is larger than 1, because this is the same as 1.25. Okay, so the growth one, when it says it increases by an amount, you have to put the 100% in there. Now the other one is kind of interesting. Now it's decreasing, it's a decay. Again, the figure is not 25%. Because what we have to multiply is how much is actually left each time. So in a decrease, instead of adding the 25% to 100, you take 100% and subtract the 25%, and that's 75% or 0.75. So this is the decay. It's smaller than 1. But what you have to really figure is what is left. And so if you just think of if it decreases or increases, if that's the wording, you have to either add it to 100% or subtract it from 100%. So when you're reading these problems, you need to make sure to look and see if it increases, then you're adding it to 100%. If it decreases, you're subtracting it, because decrease really means subtraction. Increase really means addition. If I increase something by 5, I'm adding 5. Okay? If I decrease something by 10, I'm taking 10 away. Okay? If I decrease the amount of M&Ms in the bowl by 10 because I ate them, I subtracted 10 from the bowl. Okay, so that's why you have to remember what increase, decrease means and think about those terms because those are the words that we're using. Okay, the last thing is looking at graphs, we can look at them to see that they are the different types of graphs you will get. Okay, we're going to start with the decay function, which is between 0 to 1, okay, fractional exponents. Then we're going to do a no change function, which is a 0 base, okay. Then we're going to do a growth, which is greater than 1, okay. Our growth graph, we've already done some of these, looks basically kind of like that. Goes up. If you were to go back this way, it gets smaller and smaller and smaller like that. Okay? That part's really not as important to us because growth we mainly, when we're talking real things, we're really looking at this positive growth. Okay? A change of 0 means that it's going to have no change whatsoever. So that's why, whoops, I shouldn't say change of 0, it's a change of 1. Because there's no change, right? If I take 1 to an exponent, it never changes. If I multiply by 1 repeatedly, you still get the same number. So it is not a growth or decay, it's a no change. So a base of 1 is really no change. Okay. If your base is a fraction, it's between 0 and 1, a proper fraction. It's a decay function, and we start high, and then we come down and gradually go like that. Now, theoretically, if I cut something in half, and in half, and in half, and in half, and in half, I never get to 0, do I? I never quite get to 0. But remember, I say it gets so small that we basically say, okay, there's 0 left. Okay, and so that's what happens, but that's way out in the future. But theoretically, it never gets to 0. Means you never have a time when you don't have some drug, some antibiotic in your system, because it theoretically did not get ever to 0. But that's not really true, because there's just so few now. It's so small that there just isn't any left. Okay, by the,
Yeah,
practical purposes, yes.
Is that how like all medication works?
That's how
is
all medications
half-lives?
work, half-lives. All medications have half-lives.
How come?
I don't know, ask God how that works. I'm not sure. I never have, that question has never popped in my, how come? I think, this is why I think, okay, you want me to give you my opinion?
Yeah.
Okay, so my opinion is, I think it's your kidneys or liver, whichever one takes out medication, okay? As the blood goes through that, the first time it goes through, it gets a lot of it, because there's a lot of them, so it gets half of them. Well, now you only have half left, so they're not as frequent. So in that next set of hours, it doesn't take out as much, it's only half as much, because now we only have half as much in our body. The liver can only take out half of what's there. Okay. Now we have a fourth of what was in our body before, and it can only still take out a half, that liver can. And so, because when it goes through it, it can't pull all of it out, it can only pull part of it out. That's my theory. Okay, so I think that's a pretty good educated guess for why it is. Half-lives of carbon, I am not sure if it really decays by half-lives, but that's what the experts say. I don't know that we can go back and really say what the half-life of some of these are. Some of them, they say they're 5,000 years. I want to know how they measured something 5,000 years ago and now to get that difference, okay? It's assuming they know based on what's around it, what year it came from. So yes, it could be based on what kind of culture, what it talks about, that kind of stuff, so you can get a good approximate age of it based on that. Then they use how much carbon's in there. But again, my question is, how was it held? How is it, what kind of conditions attacked that piece of paper or whatever? And then, so does that apply to all conditions? So those are questions I have about some of the carbon dating, just because we can't go back and actually prove that. Okay, we can see what it's going at now, but if we say it's a half-life of 5,000 years, if we look at it for 100 years, that's a very small proportion there. And that doesn't mean it's really going to go that amount. Okay, and I don't even know if it comes out as half-lives. That's another question I have. How do we know they come out as half-lives? I'm not sure. It may, but it's not your kidneys or your liver doing it. So it's just and my big question is, what are the elements, what's surrounding it would cause it to do that? And if it's in a sealed case, would that be different than if it's in dirt? Would that be different if it's exposed to the elements all the time? So those are questions I have on that, okay? Okay, so this is what we're gonna look at. We're gonna take a break. We'll come back and we'll do some problems up on the board today. So 10 minutes and come back. While you're taking a break, I'm looking at your notes, so leave them open. It's okay, just leave it open, I see it. I'm assuming if you have a second page, you have a first page. Good job. How's your notes?
I've got one page.
Okay. Yeah, I think I'll give you a half for notes today, okay?
Me and Gracie basically the same thing.
Do ya? Yeah.
I think it was coffee.
Yeah, I see it, okay. Okay, got that. I'm gonna eat something.
Not a bad idea.
And it's next time. Oh yeah, I did Abby today. That'll keep for later. I gotta finish my coffee. I haven't finished my coffee yet. No. Okay, Russ, you can just sign the problems to them up at the board.
Oh, the ones that I have here?
Yep. You just have them do one when most of them are done, or if they get done, you can give them the next problem. And that way or the pairs or whatever go through. We have 1, 2, 3, 4, 5, 6. We'll just have 3 boards with 2 people on each.